So here we are again for the second part of the series about time and space now. And first I want to say a few more words about what I said before. Time is not what the clock measures. We have seen here that time in our observations started already when we were sort of multicellular things. But what does the clock measure? Well, the clock measures the rotation of Earth, the orbiting of the moon, the orbiting of the Earth around the sun. These are all things we use in time. But also vibrations in a crystal and the frequency change in some AC/DC current and subatomic movements in atomic clocks, which are perhaps the most precise. But all these things are motions in space, which is already taught as existing and as described in physics. And so I call that the configuration space. That is the space, not the abstract space, but the space where particles can move. And Einstein, the manifold is really something about some kind of configuration space. So what the clock measures is just some movement, periodic movement, in some configuration space. And then there is a speed involved. And all these things are effects of time, but of course, it is not time at all. Time is completely different from that. Now, if you then say that, I read some physicists saying that, well, at the speed of light, time stops. Of course, that's nonsense. Time is the ordering, and it doesn't stop when something reaches the speed of light. But of course, in the metric, the distance measuring for the manifold that they use in relativity theory, they have a quadratic form where there's a 4-dimension time, and in the quadratic form there's a factor minus c squared t squared, with a minus sign, not plus. Normally it is the sum of the coordinates squared. That is, and then take the square root for the distance. But if there's a minus sign, there's some things happening, because sometimes this goes to 0 and so on. So, and that is all these effects which are used in relativity theory are in fact forced by the metric. And the metric comes from Minkowski space and was defined first. So Einstein said himself, and I find that a quote which they should quote more, he said, "How often was I puzzled by the manifold, or did I wonder about the manifold?" Because the manifold comes out of nowhere, it is like God-given, and there is a minus c squared t squared there. Why? And then you develop the whole theory, and you can approximate measurements and experiments, so fine, but there's still no good reason to do that. So I will not do that. So that's what the clock measures. Then I have to say, I will follow now and then, because I have to stay within the frame for the lectures. I will follow this if I can. So now we have a process in reality. Time is a stepwise process, stepwise. In time. So abstractly I can just say, well, there are some ingredients and a relation. So some ingredients x, y, and some relation x, r, y, for example. But usually people will write this relation as x arrow y relation. Then in physics and in reality, what we observe, we try to explain by causality, by cause and consequence. So cause first, consequence next, from the principle of the order. So causality is a good relation. And it's a special case of a partial order. Causality is a partial order relation that we defined abstractly. And it is the same as logical implication also a partial order, but they are special partial orders, of course. So the process in time can be very abstract, just given by some things, a set of things, x and y and so on, and some relation, which I denote by an arrow. A relation mathematically is a relation is a set of ordered pairs. Relation. So the first is x, y. The first is x, the second is y, then I draw it like this, x to y. Yeah. That's then the relation. I put that in R here and say that's the relation. In causality and logical implication, we know by our language what that means. So that is a partial order with a specific partial order. So partial orders are very important in both in physics, mathematics, and in fact in all sciences, I would say. Okay. So in time, I said it's a total order. What are the ingredients? Well, the ingredients are moments. Oh, sorry for the noise. So in time, the ingredients are moments. And I will, for the universe, I have to define something now which is going to be objects and so on. So for going into the direction of the definition of a universe, I will look at the universe U, and this will get more and more structure as the lectures will continue. And I'll begin by looking at UT, a state at moment T. That's a state. So what does this mean? We don't know yet, but it is something. It's a set. Do I put some geometry on it? Later, perhaps. Perhaps. You can. Geometry. Topology. Or more general. I would say non-commutative topology. That's the one I prefer because it's the weakest. The others, of course, geometry is usually over the real numbers. Topology is not using numbers that much, and non-commutative topology is a very weak version of topology. So I will later put states with some geometry on it. But I already say now, what I do is completely ad hoc, and I would not really do that, but I need later to define places, because we observe something and we think this is in a place. The thing being somewhere defines what we call a place, but what is that? A place does not exist, it's an abstract thing that we define. So all these things, whatever geometry you put in a manifold, you can put up, we can put for UT some space-time if you want. And you can always take the same, always the same. That's what you do in physics. I'm going to make a dynamic model where all the UTs may vary, which is probably closer to reality. So, you can do that, but it is ad hoc, and it is just later for doing experiments and using something in the description that you get geometrically to talk about places, and dynamic places will be the. So I will do this too, but I will not take the same. I will not take the same state of the universe. The universe changes, pantarei, as the Greeks said, and this is exactly the theme of most of my talks. Everything changes. So I will have a system of, and so I have something I will call a map from UT to UT prime. If T prime is bigger than T in time. So a later moment and any other moment before it, they are related by some system of maps. The UTs are sets, so this just means it takes an element from the set to an element of the set. These are maps. These will not be later for objects. For objects we will need something different, not maps but correspondences. But I will define that in a moment, or well, next time perhaps. There are two conditions for these maps. If I take t prime equal to t, then the map from ut to ut is the identity. Then you don't change anything. If you stay the same, you don't change. That's normal. But then, if I have 3, this is kind of transitivity. If I have 3 times related by the order, so t is the smallest, t double is the biggest, and t prime is in between, then I have some composition of them. So I can take gt to t double, and I can go first from t to t prime, and then from t prime to t double. And this is composition. So I go from ut to ut prime to ut double, and this is g t prime, g t prime, t double, and this is g t double. So the composition of these two steps is the third step here. Yeah, misschien is that the last. Oh, yeah. Okay, fine, we'll see. This means that it's not an arbitrary set of maps. They satisfy something which are called path independence. Because the result of going from t to the future moment t double, it does not depend on the way you choose in between. So this is path independent. Which is very logical when you have a total order. If you don't have a total order, you have another diagram, which these are the only thing you can get is sort of linear. Everything is either larger or smaller than the other, so they are ordered, well ordered, not well ordered, totally ordered. But you can also do something path dependent, and I looked a bit at that. Then you only use the partial ordered time. You don't assume the totality, and you get path-dependent developments in the universe, which makes it very chaotic, because there's some Hasse diagram for partial orders, which I'm not going into, but the logical structure for a partial order is sort of a complex diagram, whereas for the total order is sort of a linear system. And the linear system is just that the composition is the same thing as the general the composition step. So that is the conditions on the G. Okay, then there's another question. Intervals. I have to erase the blackboard a bit. Is there an eraser? Yeah. This is real practice like in the old days, not on the computer or on the screen. This is how we did mathematics in the primitive times. I think it will be fine. Okay. Now I have to go further with the objects and define them by some structure over the universe. I have some kind of geometry already, but I have no way of describing places. So I have to do that too. So let's go in that direction. There is a process time. Process step by step. You can say that going from step A to step B is one step, and then you have a time in the process defined by the steps between the ingredients. But this is not the time that we have in the universe, the ordering of the universe. So there's a chronological time. So processes can have two times. Like a biological time would be something like a step time. right? And the universal time is the chronological time, let's say. Okay, so that is the thing about time. Is there a beginning of time? I don't suppose that there is a beginning, and also say there is no beginning. So it's open. And that means that the universe can exist forever and go back and maybe expand and shrink again, or just develops from zero, or not zero, from minus infinity to plus infinity, if you want to say it like that. But it doesn't matter. The processes are there. And now I have to define what is changing in the processes. What are the ingredients now for the changes of objects? So I'm going to say, when you look at nature, you see an elephant walking there, and then in physics you embed this elephant in some geometry, because your particles move on a manifold and the elephant is consisting of particles. If you want that, fine, but that's not correct. There's no elephants walking around in some geometry. So I have to do something else, which is something that I used in sheaf theory, the idea of sheaves and local and global effects. So that's what I need. So I will define over a UT. So this is in a moment. I define some set of things. So I use a lot of sets, in fact. So I ST. And I have a map from set ST to UT. And these STs, I call them momentary potentials. Now, I want to introduce also time intervals. And that is a bit unusual like this. So this means all t double between t and t prime. And t prime are included intervals. Okay, these intervals are going to be very essential in defining existence and in the sheaf theoretical interpretation, if you like. So now I have these I have here maps to UT prime. So I also have an ST prime there, and I want to relate the potentials here, T, to the potentials in ST prime. Yeah. So how will we do that? Well, first of all, let me say, if you see an elephant or whatever, and you try to go back in time, you see that some particles come from somewhere else, and you see the whole elephant being constructed from ancestors to parents and so on. So you try to go to a moment, the existence of the elephant, not in history, but also in a moment. There is no existing thing in a moment, we will see. But there is some germ of existence. It is like take a smaller, suppose something exists over an interval, this is going to be the definition I will take. And then you make the interval smaller and smaller and smaller, converging to t. At each time there is something in the structure which is there but does not exist. So the potentials do not exist in a moment, nothing will exist. In an interval there may be. So these potentials are sort of germs of existence. Good, but that means we have to relate the ST and the ST prime, because we want to see the change between the potentials leading to the existence. So we want to change, so I'm explaining it maybe too detailed, but there may be more sessions than that, but okay, fine. Change to existence. The germs we're going to change to existence, but how do they change? For the states, I have a geometry or a topology or a non-commutative topology or some set of maps with this uniqueness property for the composition. So I will introduce now from ST to ST prime, and that for all t smaller than t prime, and for all t and t prime. And I will call this map ST t prime. And it's not a map, I said this map, it's not a map, it's going to be a correspondence. So, a map, as used in set theory and in geometry and in everything in mathematics, takes one element to one element. A correspondence takes a set of elements to a set of elements. So, correspondence maps a set, a subset to a subset. So, I take an AT. This is a subset, and it maps this AT to an AT prime. So in other words, you can think of a correspondence as a map of on the power sets. So if I have X set, the power set Px is the set of subsets of X. All the subsets of X, X included, and the empty set included. The empty set also. This is the power set, and a correspondence is a map from subsets to subsets. So correspondence is a real map from Px, a map from Px to Py is correspondence for X2. So, but this is, it looks strange perhaps. Why don't we take maps? Well, because existing things exist of many things. And I have in my body many existing things, some bacteria, some viruses, many cells, whatever, structures. So, if I would later define some existing things by only elements, that would be points, nothing will exist. So, it's very essential that I do this with sets. And so I have to not take maps, but correspondences between these things. So, first of all, now we will look at some sequences. So, in an interval, we have some sequence AT is in PST. So, it's a subset of ST, and it maps by ST T prime. And I call the image of that, this is a map, it has an image, A T prime. It's a map on the P, not on the S. So, I now get a system like I have for the UTs, but for the subsets here. A system, and I do the same condition. The composition of the two is the ST. So that whether I go this way or that way is the same. Yeah? So I have, just like I have some system of geometric, topological, or whatever maps, I have a system of correspondences above it. And now I go define existence. I will say that such a system, so I have now strings of ATs, many connected subsets. And I will look at such a string over T1. That's a time interval. This string of potentials becomes existing. an existing thing. So these non-existing things in moments and in short strings, the string is too short, it will not exist. So in a string existing thing, this is then an existence interval. Existence. That's only a name. So if you have a series of things and it exists in the interval, then the interval is called the existence interval. Okay? So now I see, I have a definition of existing, that it is a series of potentials. The potentials are germs of existence, as I said, and they begin to exist not in a moment, but at an interval. Existing thing at, very important, the interval, the existence interval. So, I don't say that an object exists in a certain moment in the interval. I don't say that it exists at the end of the interval. That's not true. It exists at the interval. And this is a thing that non-mathematicians will a little bit scared, maybe a bit scared of. What does it mean? It means that if you think like this, these intervals of existence are really the existence moments. They act as the interval. Oh, I'm going too far. The existence interval is, by way of speaking, an existence moment. It is the smallest thing where, too far.
No.
Okay, good. So you think of this interval as one existence moment. In mathematics, you would use some kind of quotient structure, but I'm not going to explain that. Quotient for sub-ideals or subgroups or sub-things. You can do that abstractly, but I will not mention it. But that's really what's happening. You take a quotient for an existence thing is not the series in moments, but the series of existence moments with at each existence moment an existing thing. So I think this is the place to stop here for today, for this section. And we have now defined a definition of existence where the existing things are not inside the states with the geometry, but are above it. And this is sort of étal, an étal space. This is going to lead to an étal space is like etallated, like in a window, and you see something there. It's in the etage, I think they say. I don't know, but it's étal. So the space I use will be an étal space over the universe. And the universe is then this structure, complete structure. It's not just the use, it's this structure. So this leads to the universe U, which is U and S. Yeah, and the systems. So for the moment, we'll stop for here. Thank you. Oké, dat is. Ja, ik ga veel.